Assalamu alaikum. In continuation with the previous topic of probability, I'm going to discuss some questions and examples from the book of Sheikh Muhammad Chaudhry, which we were discussing previously. I was on example 6.15 in our last lecture, which says 3 horses, A, B, and C, are in a race. A is twice as likely to win as B, and B is twice as likely to win as C. What is the probability that A or B wins? Now, in this question, first of all, which we can observe very easily, that the winning chances of all 3 horses are not same. And if we observe that which horse has the least chance of winning, then we can see that it would be probably the horse C. Because it is given that A is twice as likely to win as B, it means A has more chances than B, and B is twice as likely to win as C, and B has more chance to win as compared to C. So it means the least chances of winning will be of horse C. So what we can start with, as you can see here, we started with by noting probability of C by ourselves, that let probability of C be equal to P. So when it is given that as the chances of winning of horse B are twice as likely as of horse C, so what we can say that the probability of winning of horse B are twice as likely as C. So as probability of C is denoted by P, so we can write that probability of B will be 2 times P. So the next, it is given that the A has twice as likely, A has chances of winning of twice as likely as B. So it means A has twice more chances of winning as compared to the winning of horse B. So what we can do here, when we place the probability of probability of B, it becomes 2 times into 2P gives us 4P. Now, as it is given in the question that the probability of winning of all these 3 horses is not same, so which means, and they are mutually exclusive, because it cannot also happen that any 2 can win together. So there's nothing common in between them, and side by side, they are exhaustive events as well. And we know that exhaustive events are those events which collectively makes the entire sample space. So by using this property of collective sample space, when we know that those events which makes collective sample space, probability of A plus probability of B plus probability of C makes the entire sample space. All right. And we know that the probability of entire sample space is 1. So probability of entire sample space is 1, and when we substitute all these values of P, 2P and 4P, as you can see here, it gives us, and by solving it for P, it gives us the value of 1 by 7. And by substituting the value, when we substitute the value of P here, then probability of B becomes 2 by 7, and probability of A becomes 4 by 7. Now we got the probabilities of all. Probability of C is 1 by 7, and B is 2 by 7, and A is 4 by 7. Now the question is, what is the probability that A or B wins? So whenever we are asked with the probability that this event or this event will occur, I told you that we need to find the probability of A union B. So as these events are mutually exclusive and they do not have anything in common, so we'll be left with the law that will be probability of A plus probability of B. It means we can find the probability of A union B by adding up the 2 individual probabilities, which we find here, 4 by 7 and 2 by 7. And by adding them up, we can have the value of 6 by 7. So this is how we can solve this question. Now I'm going towards the exercise of this question, this exercise of this chapter, and directly referring you to the question 6.13, which is saying, find the probability for each of the following events. An odd number appears in a single toss of a fair die. Now, as we know that when we toss a fair dice, how many possible outcomes are there? We know that there are 6 possible outcomes in tossing a fair dice. And the event which we are interested, it is odd number appearance. So first of all, we'll define an event. Let A denote the event that at odd number appears. And now we'll enlist all those possibilities which will exist in event A. So how many odd numbers are there? We can see 1, 3, and 5 are the odd numbers. And then by definition of the probability, which we know very well, that probability of any event A is equivalent to the number of sample points in that event divided by the total number of sample points in your sample space. So there are 6 sample points in your sample space, and there are 3 elements in your event A. So by substituting these number of elements in the numerator and the denominator, we get the value as 1 by 2. Now the next question says, what is the probability that the sum 8 appears in a single toss of pair of fair dice? Now, first of all, we need to identify the sample points. When we throw a pair of fair dice, first of all, we need to observe that how many sample points do we have in throwing a pair of fair dice. So in throwing a pair of fair dice, we can have 6 in one dice, 6 outcomes, and in second dice, we also have 6 outcomes. So it becomes 36. It means the number of sample points in throwing a pair of fair dice becomes 36. So N of S is 36. Now we need to observe that sum of 8 appears. So when we construct or enlist all those possibilities, all those pairs, then and by observing or extracting only those pairs which have sum 8 are 2, 6, 3, 5, 4, 4, you can see. So there are 5 pairs who have their sum as 8. So by using the definition of probability, that probability of any event A will be equivalent to the number of sample points in that event divided by the number of sample points in your entire sample space. So in entire sample space, we have 36 sample points, and in that in our particular event, we have 5 sample points, which becomes the resulting probability after substituting their values. Now, the next probability which we have to find is at least one head appears in 3 tosses of a fair coin. Now, when we toss a coin, first of all, we need to observe that how many sample points we have when we toss a coin 3 times, or when we toss 3 coins at a single time. So it means, first of all, we need to identify our sample space. So in tossing a coin 3 times or 3 tosses of a coin, we have 2 possible outcomes for each. 2 for the first time, 2 for the second time, and 2 for the third toss, which becomes 8. So first of all, which we identified is the number of sample points in tossing 3 tosses of a fair coin. And if we enlist those sample points, we can see that what will be those sample points. We can see here that these are the 8 possibilities in which we can toss a coin 3 times. So these are the possibilities. Now the question demands that at least one head appears. So at least one head appears means that there can be one head in a tossing it 3 times. There can be 2 heads in tossing 3 coins, and there can be 3 heads exactly in 3 tosses of a coin. So we enlisted all those. At least means 1 head or 2 head or 3 head. So I have you can see that all these possibilities are enlisted here, excluding the possibility that there will be no head. So we can observe that there are 7 sample points in this event, and there are 8 sample points in the entire sample space. So by using the definition of probability of any event A, which we defined here, that at least one head appears, we can find the probability of 7 by 8. We can also use the law of complement here, which I told you in your previous lecture. So, but this is also the way how you can solve it. Now, the next question is, what is the probability that a king, ace, jack of clubs, or queen of diamonds appears in drawing a single card from a well shuffled ordinary deck of 52 cards? Now we need to observe that how many kings. First of all, obviously we have to select that in drawing a single card from a well shuffled ordinary deck of 52 cards. So it means, first of all, we need to define our sample space. So because we have 52 cards and we are going to draw only one card from here, then the possibilities in your sample space will be 52 only. 52C1 means 52. So now we have to find the probability that what is the probability that it will be a king, ace, jack of clubs, or queen. So basically we'll add up all those. So there are four cards of king in the entire deck of cards. There are four aces, and jack of club is only one, or queen of diamond is also only a one card. So by adding up all those, four king, four aces, one card of jack of clubs, and one card of queen of diamonds becomes 10. So 10 means there are 10 sample points in your event A, which you defined as that the card selected will be a king, ace, jack of clubs, or queen of diamonds. So there will be some 10 sample points in that particular event. And when you substitute the values of the sample points in the definition of any event to find the probability, that number of sample points in your entire sample space, which are basically written under in denominator, and the number of sample points in your event, it becomes 10 by 52. Now we move to the next question. A marble is drawn at random from a box containing 10 red, 30 white, 20 blue, and 15 orange marbles. Find the probability that it is orange or red. Now we can find it very easily. First of all, we need to identify that how many total marbles are there. So I write the colors of all: red, white, blue, and orange. And there are 10 red, 30 white, 20 blue, and 15 orange marbles, which makes the sum of total 75. And we need to draw just one marble from it. Okay? So first of all, we need to define our sample space, which becomes, out of 75, we need to draw only one. So it means 75C1 gives us 75. So which makes 75 as our sample space for this event. So we have 75 as our sample space in this event, in this particular question. Now the first one is the probability that, what is the probability that the selected marble will be orange or red? So it means you have to find the orange or red. Now what you will simply do, you will add up the numbers of orange and red. So there are 15 orange and there are 10 red marbles. So when you add them up, their probability becomes 25 by 75. So which you can see it here, which becomes 1 by 3. The probability of a marble is orange or red. Similarly, we can perform the next one. Probability that marble is not red or blue. Now we'll exclude the red and blue marbles from it. So excluding the red marble and the blue marble, which makes a sum of 30, we are remaining left with 45. 30 white and 15 orange becomes 45. So marble is not red or blue, we can get the probability of 45 by 75. Now the next part is, what is the probability that marble is not blue? So marble is not blue means we will exclude only this color of marble, blue marble, out of the total. So when we exclude this 20 marbles from the total, becomes 55. So 55 divided by the total number of sample points, which are in your sample space, just 75. So we can find the probability that marble is not blue. Now the next question is, what is the probability that marble drawn is white? So what we'll do, we'll only pick up those number of marbles which are white. So there are 30 white marbles out of the total. So the probability of finding that the marble is white is only 30 by 75 by definition. Now the next is, what is the probability that the marble selected will be either red, white or blue? So what we'll do, we'll add up the marbles of red, white and blue color, and by adding these up, we got the sum of 60. So by the definition of probability, which says the number of elements in your samples in your event divided by the number of elements in your sample space. So by dividing the two values, we get 60 by 75 because the sum of these colors of marbles makes the sum 60. So we can find the probability of this question very easily. Now the next question is, a box contains 6 discs numbered 1 to 6. Find for each integer k from 3 to 11 the probability that the numbers on 2 discs drawn without replacement have a sum equal to k. Now first of all, what we need to observe here, that how many discs are there. So what we can see, that there are 3 discs, 1, 2, 3, 4, 5, and 6. So we enlisted all the discs here which were numbered 1 to 6, and we are given with that for each integer k from 3 to 11, the probability that the numbers on 2 discs drawn without replacement have a sum equal to k. So k stands for the sum of the 2 discs drawn. Sum of the 2 discs drawn out of 6. First of all, obviously we'll need to observe that how many sample spaces are there. Obviously we'll see it also. So first of all, what we'll do, we will write the sample space, the possible sample space, that when we select 2 discs at a time out of the 6 discs, it becomes 6 possible ways will be 6C2. So 6C2 gives us 15. So 6C2 gives us 15. And when we make the possible pairs, that in how many ways we can select these 2 discs out of 6 discs, the possibilities are 1, we can see 1, 2, then 1, 3, as you can see here, 1, 3, 1, 4, 1, 5, 1, 6, like 1, 2, yeah, you can see here, then 1, 3, 1, 4, 1, 5, and 1, 6. So by enlisting all the possibilities of pairs, that in how many ways we can select the pairs from these 6 discs are enlisted here. So when we count these possibilities, there are 15 possibilities. All right, now K stands for the sum. So when the sum, if we enlist the values of K from 3 to 11, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So now what will be the probability, how we can find the probability that K is 3. So now how many possibilities in the pairs, you can see whose sum is 3, because basically C stands for the sum of 2 discs. So we can see that there is only one pair which has the sum 3. So what we do, that by using the definition of any event A, when the sum is 3, and for example, I use the same notation which I told you previously, n of A divided by n of S. So n of A means there only one possibility, means only one pair which has the sum as 3. So and dividing it by total, which is there are 15 possibilities, it becomes 1 by 15. Similarly, how many pairs have sum 4? There is only one pair which has sum 4. So it becomes 1 by 15. Now for k equals to 5, how many pairs are there which have sum equals to 5? So here is 1, 4 which has sum as 5, and 2, 3 is also having a sum as 5. So there are two pairs which are having the sum as 5. So the probability of k equals to 5 becomes 2 by 15. So how many pairs have sum equals to 6, for which the k is 6? Then there are two pairs which have sum as 6. You can see it. Similarly, how many pairs for which k equals to 7? That means how many pairs are there for which the sum is 7? So there are three pairs. You can see 3, 4, 6, 1, and 2, 5 are the three pairs which has sum equals to 7. So similarly, we can find the probability of all these sums. And if I lastly observe, for example, for probability of k equals to 11, I can see that there's only a one pair, 5, 6, for which the probability is 1 by 15. So this is how we can find the probability that for the integer k from 3 to 11, which stands for the sum of two disks selected at a time, we can find their respective probabilities here. Now the next question is 6.18 question from the again the Sher Mohammad Chaudhary book, Introduction to Statistical Theory. In a single throw of two fair dice, find the probability that the product of numbers on the dice is between 8 and 16, both inclusive. Now again, first of all, for any question, we first need to define the possibilities in our sample space. So which we can observe that in our sample space, because we have two fair dice, and we know that in tossing two fair dice, we have 6 by 6 probability of 6 by 6 sample points in our entire sample space, which becomes 36. And you can see that I have enlisted all these possibilities here. The 36 pairs in throwing two fair dice. All right. So now we need to observe what is the probability that their product of the numbers appearing on in these possibilities will have the product between 8 and 16. So we will identify first of all, let A be the event that the product of the numbers on the dice is between 8 and 16 inclusive. So now we'll identify all those pairs whose product is between 8 and 16 included, like 2 4s are 8, 2 5s are 10, 2 6s are 12, and then 3 3s are 9. So there are many pairs. And how many pairs are these? There are 12 pairs for which the sum is between 8 and 16 inclusive. So you can identify all those pairs for which the sum is between 8 and 16, including them, are 12 sample points. So by using the definition of probability for any event A, which was defined here as the product of the numbers on the dice is between 8 and 16, that will be n of A by n of S, and which gives us probability 12 sample points in event divided by 36 sample points in your sample space. So this is how we can find the probability of the first part. Now there is the second question, which says what is the probability that the product of the numbers will be divisible by 4. Now we'll find out all those pairs whose product is divisible by 4. So let B be the event that the product of the numbers on the dice is divisible by 4. So we will extract out from this sample points all those possibilities whose product will give us a number that is divisible by 4. So we can have that all those pairs, you can see them, that all these pairs are those which have their product divisible by 4, which are total 15 sample points, which may be collectively exist in this event B. So by using the definition of probability of B, we can have the probability as n of B divided by n of S, which becomes 15 by 36. Now moving to the next question, 6.20. From a pack of 52 cards, 2 are drawn at random find the probability that one is a king and other a queen. Now, first of all, obviously, we need to observe that how many sample points will exist in performing this experiment or drawing these cards. So 52 cards are there, and we are going to draw 2 cards from it. So we will have our samples point as 52C2. These are the possible ways in which we can select or draw 2 cards from a deck of 52 cards. So there are 1, 3, 2, 6 points, sample points in this experiment for the sample space. Now the probability that to find that one is a card and the other is queen. So what you will do here, that you will need to observe that how many kings and how many queens are there, queen cards are there. So there are 4 king cards and there are 4 queen cards. So making this complete event, it means 1 card from the kings and 1 card from the queens becomes 4C1 multiplied by 4C1 gives us 16 sample points in which we can select a king or a queen from a deck of 52 cards, which makes the probability that to find the probability of any event A, which was defined here, as you can see here, that 1 card drawn is a king and other is the queen, can be found by using the law, by the definition, n of A by n of S, which gives us the probability as you can see here. So I think it's quite easy. And now moving to the next question, which is again the B part of question 6.20. A set of 8 cards contains 1 joker. A and B are 2 players, and A chooses 5 cards at random and B taking the remaining 3 cards. What is the probability that A has the joker? Now what we are given with that there are 8 cards, are there only 8 cards, in which 1 is joker. And there are 2 players which are going to take these cards, to divide these cards, in which from which 5 will be taken by the player A and remaining 3 will be taken by player B. Now, first of all, we need to define our sample space. So because we are interested to find the probability for only event A, which will select only for the player A, who will select 5 cards out of these 8. So our sample space becomes how many ways in which player A can select 5 cards out of 8 cards. So 8C5 gives 56 sample points. And A can choose, now the probability that we have to find, what is the probability that A has the joker? Now because A has to select 5 cards, and we have to find that he has the joker. So we need to know that how many jokers are there in these cards. There is only 1 joker here. So that joker card will be given to the player A. So there are 1C1 ways that out of these 5 cards which the player A is going to take, so 1 card from the joker will be given to the player A, and the remaining from the remaining 7 cards out of 8, the remaining 4 cards will be drawn for player A. So by solving this combination 1C1 and 7C4, which you can calculate in your calculator, gives you 35 ways. So by the to find the probability that what is the probability that A has the joker, so we can very easily find it by using this definition, that n of A here is 35 and n of S is 56 here. So we can find the probability quite easily, and it must be quite clear. Now the question 6.21 is here. Of 12 eggs in a refrigerator, 2 are bad, and from these 4 eggs are chosen at random to make a cake. What are the probabilities that exactly 1 is bad? So first of all, we need to find out identify basically the experiment. First of all, we'll write down what is given to us. We are given with that there are total 12 eggs, and out of these 2 are bad. So I have written it here that 2 are bad and 10 are obviously good. So we have written the distribution of these good and bad eggs. And what we are going to do, that from these 12 eggs, we are going to select 4 eggs for a cake. So in how many ways, first of all, we need to define our sample space, that in how many ways out of these 12 eggs, we can take out 4 eggs. So the possible ways which makes our sample points for the sample space, there are 12C4, 495 ways in which 4 eggs can be chosen from 12 eggs. So now the first event is that what is the probability that exactly one is bad? So first of all, we define our event. Let A denote the event that out of these 4, exactly one is bad. So how we'll find the sample points for this? We know that there are total 2 bad eggs, and we have to find the probability that exactly 1 egg is bad in those 4 eggs used for cake. So how many ways we can find the 1 bad egg and remaining 3 will be good eggs. So we know that out of 2 bad eggs, there are possibilities that 2C1 will be the possibility that exactly 1 bad egg will be included in making a cake. And out of these remaining 10 good eggs, 10C3 ways can be the रागी रागी मैं Zoom के ऊपर लेक्चर रिकॉर्ड कर रही हूँ, वो बैटरी कैमरे से 10 मिनट का होता है, इसको छेड़े ना फोन को. So there will be 2C1 and 10C3, 240 ways in which we can take out 3 good and exactly one bad egg out of these total 12 eggs. So the probability by substituting the values of sample points in your event divided by the sample points in your sample space gives us the probability of that exactly 1 egg is bad out of these 4 eggs. Now, the next part is that at least 1 is bad. So at least 1 is bad means that out of these 4 eggs, how many bad eggs can be there? Now there are total 2 bad eggs. So at least 1 means that out of these 4 eggs which we are going to use for making a cake, there can be 1 bad egg and there can be 2 bad eggs. At least 1 means, but not more than that, because there are total 2 bad eggs. All right. So how we can find the probability that I said 1 bad egg or 2 bad eggs? So how I will find the probability with that, I can also use the law of complement here. 1 minus probability that no egg is bad. All right. So no egg is bad means what I can do is that out of how I can find it, probability of B complement, that out of 10, we got all the good eggs, 10C4 equals to 210. When we find it, it becomes 210. Another way we can also find it, which I said you, that at least 1 means that there can be exactly 1 bad egg, at least 1 bad egg means, and 10C3 plus 2 eggs, 2 bad eggs, 2C2 and 10C2. So this will also give you the same answer, which will be 285. So when you solve it, you may get the value as 285. So in one way, we can also find the probability like this, probability of, if I say B is the event that there will be at least 1 bad egg. So we can find the probability like this. Otherwise, we can also find the probability by assuming the law of complement, which is explained here. Which one is like that we can also use the law of complement. There is no bad egg. So no bad egg, the probability of that no bad egg will be like 10C4, which gives us 210 ways, and 1 minus, by using the law of complement, it gives us 1 minus 210 by 495, for which you can see the probability. So I think you can solve the question in both ways. Now the question 6.22. An integer between 3 and 12 inclusive is chosen at random. What is the probability that it is an even number? Now, first of all, obviously, you need to write down your sample space. So we have integers between 3 and 12. So enlisted down all those sample points in your sample space from 3 to 12 becomes 10 sample points. So n of s will be 10. Let A be the event that the integer chosen is an even number, which is given in the question. So now we will list down all these numbers in our event A, which are even number. So by enlisting the even numbers, we can see that the sample points in this event are 5, which are from 3 to 12, are 5 numbers who are even. So by using the rule of probability, probability of A is equivalent to the number of sample points divided by the number of in your event A divided by the number of sample points in your sample space, which gives 5 by 10 as divided by 1, gives you the answer 1 by 2. Now the next part is, what is the probability that it is even and divisible by 3? So now we need to identify those numbers which are even and side by side they are divisible by 3. So first of all, we define our event. Let B be the event that the integer chosen is an even number and is divisible by 3. Then how many numbers are there which are even? There are these numbers 6, 8, 10, 12, but they must be divisible by 3 as well. So there are 2 numbers only which are divisible by 3 also. So it means on the basis of this, when we enlisted down those numbers for our event B, there are only 2 numbers or 2 elements in this event which are on the standard of or on the requirement of our event B. So by using the probability probability of B will be equivalent to the number of sample points in that event divided by the number of sample points in your sample space. So there are 2 sample points. So we enlisted it here, and there are 10 sample points in your sample space, and solving it, we can get the value. Now moving towards the next question, 6.22 C part. A box contains 4 red, 4 white, and 5 green balls. The 3 balls are drawn at random from the box together. Find the probability that they may be all of different colors. So first of all, for every question as we do, we enlist the number of sample points in our sample space. So there are total, when we do the total of all these 4 red, 4 white, and 5 green, there becomes 13 total balls. And how many balls we have to select? You have to select more than one. That means 3 balls we have to select. So in how many possible ways we can select these 3 balls? There will be 13 C3 sample equals to, which gives, after calculation, 286 possibilities are there in which we can select 3 balls out of 13 different colored balls. So this defines our number of elements in our sample space. Now, what is the probability that all of them will be different colors? So first of all, we'll define the event that all balls drawn are of different colors. All balls means 3 balls drawn are of different color. So a different color means 1 will be white, 1 will be red, and 1 will be green. So there are 4 red, out of which we can select 1 ball in 4 C1 ways. There are 4 white, out of which we can select 1 ball in 4 C1 ways. And there are 5 green balls in which we can select 1 ball in 5 C1 ways. So by multiplying all 3 possibilities, there are 80 possibilities or 80 sample points in this respective event. So by using the rule of probability and dividing the number of sample points of event divided by the number of sample points of sample space gives us the probability like this. And the second part for this question is all of the same color. Now, what will you say of them that you have to select 3 balls and we are saying that all of them are 3 colors? Now, the question arises that of which color? It may be exactly 3 red colored ball, or 3 white colored balls, or it may be 3 green colored balls. So there are three possibilities, because it is not mentioned here that 3 red balls or 3 white balls or 3 green balls. So we'll enlist all the possibilities. If we say that these 3 balls which are of same color may be red balls. So there are 4 C3 ways which we can select a red ball, all 3 same colors, all of 3 same colors. Then I said that there may be possibility that all of 3 could be white colored balls. So there are the possibility that of white color 4C3 in 4C3 ways we can select all white colored balls. And there may be also a possibility that 3 balls selected will be of green colors. So in 5C3 ways we can select all colors of green balls. So by adding up those, we can have the probability by calculations as which gives us sum of 18, and probability of B will be n of B by n of S, and 18 divided by this 286, which is the sample points in your sample space, gives us the probability. So this is how we can calculate the probability of these sample points. Now there are some practice questions which all of you students will try to do yourself, and inshallah you will be able to solve it if you have understood all these previous questions that I have told you. Now I'm moving to some other questions of the exercise. Question 6.27. A class contains 10 men and 20 women, of which half the men and half the women have brown eyes. Find the probability that a person chosen at random is a man or has brown eyes. So, first of all, I'm going to define our event. Let A be the event. We have to find: a person chosen at random is a man or has brown eyes. So if I say that A is the event that a person is a man, and B is the event that the person selected has brown eyes, so I have to find the probability of A union B, because there is written that a person selected is a man or has brown eyes. From this you can assess that you have to find the probability of A union B. So first of all, I need to visualize the given information, how I can write it. So I can construct a table in which I can see that how many men are there and how many women. There are 10 men and 20 women. And we are told that half of them have brown eyes, half of the men, and half of the women have brown eyes. So half means that out of these 10, 5 have brown eyes and 5 don't have brown eyes. And out of these 20 women, half means 10 have brown eyes and 10 don't have their brown eyes. All right. So this is the distribution of the given question which we are given with, and we need to find the probability that a person chosen at random is a man or has a brown eyes. So we need to find the probability. So probability of A, how can we find it? What is the probability that as I told you, that A is the event that the person is a man, selected as a man. So first of all, if we want to find the probability that a person selected is a man, so how we can find it? How many men are there out of total? Total persons are 30. 10 plus 20 means 30 sample points. Total persons are 30, and probability of A that there will be a person selected will be a man, there will be 10 by 30. Similarly, probability of B that a person selected has brown eyes. So we need to identify that how many brown-eyed persons are there, including men and women. There are brown eyes. How many? 5 plus 10, 15 brown-eyed person. All right. So it would become 15 by 30. And for we have to find probability of A union B, we need to observe that either these two events are mutually exclusive or they are not mutually exclusive. So they are not mutually exclusive because they may have the two qualities as common, that a person selected is also a man or he may also have brown eyes. So we need to identify the common points. That means A intersection B, that a person selected is a man and he has brown eyes as well. So we can observe from the table that there are 5 men who are also having their brown eyes. So these 5 will make the probability 5 divided by 30. So by substituting the values in this additional law of probability of not mutually exclusive events, we can get the probability as you can see it here. Similarly, there is another question, question 6.27. In a group of 20 adults, 4 out of the 7 women and 2 out of the 13 men wear glasses. What is the probability that a person chosen at random from the group is a woman or someone who wear glasses? Now, starting with a given scenario, we need to find the probability that a person selected at random is a woman or someone who wear glasses. So there are 2 events given to us. A person selected as a woman and someone who wear glasses. So we define 2 events. Let W be the event that the person chosen be a woman, and G be the event that the person wears glasses. And we have to find that women or who wear glasses. So it is very clear that we have to find the probability that women or wear glasses becomes W union G. So if we make the table of the given information, we get the table as of those persons. How many women? There are 7 women. Out of them, 4 wear glasses. It means remaining those who don't wear glasses are 3 women. And out of 13 men, 2 are there who wear glasses and 11 are those who don't wear glasses. So you can see it from the table very well, the distribution of the given information. Now we need to find the probability that a person selected is a woman or who wear glasses. So probability of selecting a woman, what it would be? There are 7 women out of how many? 20. So to find the probability of selecting a woman, we can simply divide it by n of W by n of S. So we have n of W as 7 and n of S as 20. So it becomes 7 by 20. So probability of those who wear glasses. You can see from the table how many persons who wear glasses. 4 plus 2 becomes 6. So probability of those persons who wear glasses becomes 6 out of 20, gives us probability of those who wear glasses. And now, because they are not mutually exclusive events, they may have something common, that a woman selected can also wear glasses. So what will be the probability? We can see from the table that how many women who also wear glasses? There are 4 women who wear glasses. So this becomes W intersection C, means a woman and who wear glasses. So 4 by 20 becomes the probability of intersection between the 2 events. So we can find the probability of W union G, which can be observed here, and you can find it very easily. So this is how we can find the probability of all these questions. Hopefully all these discussion and solution of these examples will help you to understand the exercise and the concepts of probability, that how you will solve it will make it easy, inshallah. Now I'm moving towards the next topic, independent events. Previously we discussed mutually exclusive events, we discussed not mutually exclusive events, what are equally likely events. Now I am going to discuss here a case in which how 2 events can be independent. Now, as the term is very clear, independent means the 2 events which are totally independent of each other, which are not the reason to affect the occurrence of the other event. For example, if I say, if I take the example of 2 coins, if we toss 2 coins and I say that the tossing of 2 coins is independent from each other. Like if I toss 1 coin and I can get a head or a tail on that coin, let that, for example, and I'm interested to observe the number of head in first coin, the occurrence of head in first coin. So the occurrence of head in first coin is 1 by 2. The probability, if you want to find the probability, it becomes 1 by 2. Now, when we toss a second coin, what do you think that would there be any influence of the tossing of first coin on the tossing of second coin? There will be no influence, because the coin tossing, the two coin tossing or a three coin tossing, these are the cases in which one coin's the occurrence of head on one coin will not affect the occurrence of head on the second coin. It means in such cases the two events are independent. So if we observe the definition, it is very clear: the two events A and B in the sample space are defined to be independent if the probability that one event occurs is not affected by whether the other event has or has not occurred. So it's in such cases when these two events which do not affect the occurrence of the probability of the other event in any case are known as independent events. All right. So independent events in terms of probability can be expressed as that the two events are said to be independent if the probability of their intersection can be written as the product of their respective probabilities. So probability of A intersection B is equivalent to probability of A into B. If any two events occur in this relation, they are said to be independent events. So probability of A intersection B, what does it mean? Now, as I told you that A union B, whenever in a question it is asked, find the probability that event A or B will occur, I told you, you need to find the probability of A union B. But for probability of A and B, A intersection B means event A and event B both will occur. Now, you can see from this example, it will help you to get this concept more clear. I'm referring to example 6.28. Let A be the event that a family has children of both sexes, and B be the event that a family has at most one boy. So, if a family is known to have 3 children, then show that A and B are independent. Then show that A and B are independent. So first of all, what we are given with, that family has 3 children. Family is known to have 3 children. So first of all, we need to write the sample space. So as it is said that A be the event that family has children of both sexes, we will write all the possibilities. All the possibilities in which you can say that a family can have 3 boys. They can have 2 boys, like this: first boy, second boy, third girl, first boy, second girl, third boy, then first girl, second boy, third boy, and like this you can have all the possibilities. I think it's quite easy to understand that as we know that there are 3 children in a family, we enlisted down all the possibilities of sequence in which a person in a family can have the children of both genders. Now we come to find the probability of respective events. A is the event that family has children of both sexes, and B is the event that it has at most one boy. Now, A is the event that children of both sexes. Now we will find out all those pairs, all those possibilities in which there are children of both sexes without considering their number. So this is the case in which both genders are present. Both genders are present. This is the case. This is the case. And excluding these 1 and 2 are the cases in which there is only one gender present, first and last one. So excluding these 2, all of the remaining can be enlisted in our event children of both sexes. All right. And the next event B says that at most one boy. At most one boy means what we can say that at least there should be one boy at most. So we wrote all those possibilities. At most means there, if we take it as in terms of statistics, that at most means there can be, at most one means there can be only one boy or there can be no boy. So we enlisted down all those possibilities of at most one boy. So at most one boy, there are possibility of one boy all these are showing at most one boy, and finally no boy. All right. Now when we take the intersection means we observe the common sample points in both. So there are 3 common sample points in set A and set B. Now for finding their respective probabilities, probability of A, how it can be calculated? The number of sample points in your event, which are 6, divided by the number of sample points in your sample space, which are 8. So by dividing both, you can find the probability of A. Then comes the probability of B. Probability of B can be found out by dividing the number of elements in your sample points in number of elements in your samples in your event divided by number of elements in your sample space, which becomes 4 by 8. And side by side, we are also able to find the probability of A intersection B. There are 3 elements in this set, and dividing it by the total number of elements in your sample space gives 3 by 8. So now to find that these events are independent events, I told you previously the law that for independence we can check this, that if the probability of their intersection is equivalent to the product of their independent probabilities, their individual probabilities, we can say that the 2 events A and B are independent. So to check this independence, what we did, we multiplied the 2 probabilities, probability of A and probability of B, which gave 3 by 8. So this probability of 3 by 8 is exactly similar to probability of A intersection B calculated from here, from this set. So it means we can say that probability that A and B, given in this part A, are showing that A and B are independent event, because this property, which I mentioned here, probability of A intersection B is equivalent to the product of their respective probabilities, is basically setting true in this case. So we can say that A and B are independent. Now the next part is that you have to again observe the same. Let A be the event that family has children of both sexes, and B the event that family has at most one boy. If a family is known to have 4 children, then we have to show that A and B are dependent. It means we have to show that there are now no more independent events. So in this case, first of all, we'll enlist down all those possibilities in which a family can have 4 children and of both genders, or all the chances. First of all, we'll write all those chances in which a family can have children. They can be 4 boys, they can be 1 girl, with all these settings. At first, like this shows first 3 boys and last girl. This is showing first 2 boys and third girl, and then again a boy. And similarly, all these respective possibilities which are listed here are the possibilities in which a family can have 4 children. Now coming up again to our event, which said that there are a family has children of both genders. So we enlisted down here all those possibilities without making any restriction that a family has 2 boys or 1 girl or whatever. We enlisted down all the possibilities in which a family have children of both genders. So from this sample space, we excluded all those sample points in which we could see that there are both genders present here, excluding the possibilities of only all the boys and all the girls. We are left with 14 sample points here in our event A, and there are 18 sample points in our event, in our sample space. All right, and now come to the second event B, which says at most 1 boy. Now I told you at most means that there is only 1 boy or there is no boy. So we enlisted down from the above sample space all those possibility in which we have at most 1 boy. So you can see there are enlisted all the possibilities from the sample space in which we have only 1 boy or no boy. So to show that the two events A and B are independent, first of all, we need to find out their intersection. So when we took intersection of A, intersect A and B from these two sets, we written down here all those possibilities which are common in both sets. So their probabilities, now we can find them. Probability of A, how we can find it? As there are 14 elements in this set A, and by dividing it, the number of elements by sample space, we can have the probability. And probability of B can we find out the number of sample points in this in this event divided by the number of sample points in your sample space. Similarly, number of sample points in this intersection set, which is 4, dividing it by number of sample points in your sample space gives us all the respective probabilities. Now to find out that either the two events A and B are independent or not, we can find the probability. We can find their respective product. So by doing the product of probability of A and probability of B, multiplying it both, it is not becoming equivalent to the probability of A intersection B, which is 1 by 4. So if the product of the two probabilities here is not equivalent to probability of their intersection, then it is quite clear that the two events A and B are no more independent events. They are said to be dependent events. So this is how we can find the probability, and we can show that either the two events are dependent or independent. Now there is one more question from the exercise, example 6.31. The probability that a man will be alive in 25 years is 3 by 8, 3 by 5, and the probability that his wife will be alive in 25 years is 2 by 3. So, sorry, this is example 6.31. So we can see 6.31. So we are given with the probabilities of a person, a man alive, probability is 3 by 5, and the probability that a woman will be, his wife will be alive in 25 years is 2 by 3. What is the probability that both will be alive? Now, both will be alive means what you have to find, that A will be alive, means the man will be alive, and his wife will be alive in 25 years. So as we know that the probability of being alive of a man or a woman, his wife, is independent of each other, because life and death of one person is independent of the other. So we can very easily assess it that the two probabilities are independent. So we can find the probability which we are asked here, that what is the probability that both will be alive. Both will be alive means A is also alive and B is also alive. So that's why we need to find the intersection. So by using the law of independence, probability of A into probability of B, we can have their respective probability that both will be alive after multiplication, which becomes 2 by 5. Now the next question is that what is the probability that only the man will be alive? So only the man will be alive means that man will be alive, but his wife will not be alive. So wife will not be alive. What will be the probability that we know that probability that a man will be alive is given as 3 by 5. And if he's not alive, we can find it by taking the complement. Probability of A complement means, this is a complement means straight line, which is the opposite. And we know that the law of complement can help us to find the opposite event probability. So 1 minus 3 by 5 will give us 2 by 5. So this will be the probability that man will be not alive, and the probability of that his wife will be alive is given as 2 by 3. And if I want to find that what is the probability that his wife will not be alive, is basically the probability of complement, which is basically the opposite of this. So by using the law of complement, 1 minus probability of B gives us 1 minus 2 by 3 as 1 by 3. So now I need to find in the second part 1 by 3. So in the second part, we are given with what is the probability that his man will be alive and wife will not be alive. So we need to find this. Man will be alive and wife will not be alive. So because these two events are independent, that death and life are of two persons are totally independent of each other. So what we can do, that man will be alive is the probability 3/5, and because they are independent, we will multiply the other probability, which is basically the probability of his wife's death is 1/3. So we can find the probability which is given as 1/5. Now the third part is, what is the probability that only the wife will be alive? So only the wife will be alive means that out of these two events, man will not be alive. Alive means he will be dead. So we'll use the complement here. And his wife is alive. So again, as we know that both the events are independent. So what we'll do, we'll multiply the probability of death of the man, 2/5, multiply by the probability of death of the probability of life of his wife, that she is alive, and that is 2/3. So 2/5 multiplied by 2/3 gives us the probability that only the wife will be alive. So we can see it from here what we need to find. And the next question is, at least one will be alive. And now at least one will be alive means, what does it mean? As I told you previously, that at least one will be alive means that a man will be alive, or his wife will be alive, or both will be alive. So at least one will be alive, its probability can be found by at least, as I told you, that it means A union B. If you remember in our previous lectures, I told you that at least or condition, at least condition, and if we are given with the or condition, we need to find A union B. So by the rule of probability, addition rule of probability, it is equivalent to probability of A plus probability of B minus probability of A intersection B. And because these two events are independent, we have also found their intersection probability as here we have calculated 2/5, that both will be alive. So by substituting all the values here, we can get the probability that at least one will be alive. All right. And there is a last part of this question, that neither will be alive. That means what we can say, that not man will be alive and not his wife will be alive. So what we'll do here, we'll simply write down that neither will be alive means not the man is alive, not his wife is alive. So we can write the probability as that we need to find that man is not alive, and alive means the complement not alive, and his wife is not alive can also be found by taking the complement. And because both events are independent, we will multiply the probability of complements that we have found previously, probability of A complement multiply by probability of B complement. So by multiplication of these two, you can see here, we get the answer of 2/15. So I think you can solve it. And this video will help you to understand the concepts. Now, there is a next question. 3 missiles are fired at a target. This is question 6.51. And as we know that hitting of target of all missiles of one missile and second missile are independent. And it is also mentioned here that if these missiles are fired independently, so we can first of all assess that the probability which we are given with 0.4, 0.5, and 0.6, which are the probabilities of 3 missiles to hit the target, are totally independent of each other. So we have to find the probability. What is the probability that all the missiles hit the target? Now, what does the statement means? First of all, we'll write down all the probabilities. A1 be the probability that missile 1 hit the target. and A1 complement will be the opposite, that missile 1 will not hit the target. 1 minus 0.40 gives 0.60. So A2 will be the probability that missile 2 will hit the target, and by subtracting it from 1 will give the alternative or opposite of this event, that it will not hit the target. And A3 be the probability that third missile will hit the target with probability 0.60, and the opposite of this will be that it will not hit the target with probability of 1 minus 0.60 as 0.40. Now the first question is that what is the probability that all missiles hit the target? So all missiles hit the target means probability of A1 intersection A2, that means first target is hitting by the missile, second missile also hit the target, and the third missile also hit the target. And because we are given that these three targets, the three missiles hit the target independently, so it is equivalent to the product of their respective probabilities of hitting the target. So 0.4 multiplied by 0.5 multiplied by 0.6 gives us the probability that all three missiles will hit the target. Now the second part is, what is the probability that at least one of the three hits the target? At least one means, you know it very well, at least one means at one side we can say that one missile hit, or two missile hits, or three missile hits. Now, as this question becomes quite long to solve, the other option is that what we can use, the alternate way, is that we use that no missile hit the target. So by subtracting it from 1, we can find the probability that at least one of three hits the target. So what we can find, 1 minus probability of no missile hits the target, it becomes that first one doesn't hit the target, second missile doesn't hit the target, and third one doesn't hit the target. And by subtracting it from the multiplication of these three independent events, we can find the probability of at least one of the three targets, of the three missile hits the targets. So this is how we can solve this question alternately and in a easiest way. Now the next part is that exactly one hits the target. Now exactly one hits the target, what does this mean? If I ask you that which one hits the target, you will say missile 1 may hit the target, missile 2 may hit the target, or missile 3 may hit the target. कोई भी hit कर सकता है. So we wrote all the possibilities which you had in your mind, that if missile hit the target, missile 1 and missile 2 and 3 didn't, then second possibility that missile 2 hit the target and missile 1 and 3 didn't, and the third possibility that missile 1 and 2 didn't hit the target but missile 3 hit the target. And because they are all independent of each other, and that's why what we'll do, we'll make the product of all these possibilities, and by adding up the product of all these possibilities, we can get the probability that exactly one hits the target. And lastly, what is the probability that exactly 2 hits the target? So exactly 2 hits the target, the question again arises, which 2 missile exactly hits the target? You will say that may be first or second one, that may be first or third one, that may be second or third one. So because we are not exactly mentioned here that which missile, first or second, whatever, we are not given with. So we'll write all the possibilities that in which 2 missiles will hit the target, A1, A2, or A1, A3, or A2 and A3. So what this statement means that A1 and A2 hit the target and A3 didn't hit the target. Similarly, this shows missile 1 hit the target, missile 3 hit the target, but missile 2 didn't hit the target. So this is coming up to this, according to the question, that exactly 2 missiles hit the target. So because all these events are independent, by taking the probabilities of the respective hitting the targets and adding them up, you can find the probability that exactly 2 hit the target. So with this discussion, we have come to the end of this chapter, and I hope all these previous discussions will help you to find and solve these all the exercise, and it will also help you to make clear your concepts of probability. Thank you.